All right, mathletes, let's dive in here and let's look at the binomial. Not binomial, the central limit theorem, but for proportions. All right, we already talked about the central limit theorem, but let's dive in here and let's look at proportions. So let's go ahead, let's share my screen. And before we start, how are you doing? Well, enough about you. Make sure you smack that like button. Let's get started. So smartphones here. You got a poll agency reports that 52% of teenagers own a smartphone, right? That I think is probably higher today than whenever they did this, right? Everybody has a smartphone now. It's crazy. So what they're giving us is they're really giving us the mean. All right. So when they ask us in part A for the mean, we're going to be writing this down. And again, you're going to be writing down some formulas in a few minutes. So make sure you get your pens and pencils ready. And they also tell us that we have a random sample of 200 teenagers drawn. And that's going to be important too. We're going to need the sample size for these formulas we're going to look at. All right. So remember, when we used the central limit theorem before, we had a bell-shaped curve. We had a normal distribution, right? Here, that's going to be something that we need to check for. And again, we're going to walk through all this. So be patient. All right. So the first thing, whenever they ask you for the mean of the sampling distribution, that's just the probability that that will happen. So there it is. P equals 0.52. Right? So there it is, 0.52. Our standard deviation, we're going to use our calculator here to see how they do this, right? So the standard deviation of the sampling distribution, here's our formula, right? So we take the square root of P, which we found to be 0.52, and we're going to multiply that times 1 minus 0.52, and we divide it by the sample size, which is going to be 200. So again, write down this formula. So every time we're looking at the central limit theorem for proportions, this is our formula. All right. So let's get our calculators. Let's look at our calculators and let's plug this in. All right. So let me share the screen. Let me remember these numbers here. What's our n value? Give me a second. Our n value we said was 200, just so I don't forget. All right. So we're going to go to second square root. You're going to put your p-value, which is 0.52. I'm going to do parentheses, right, which is right above the 8, the left parentheses. I'm going to do 1 minus 0.52, close parentheses, and we're still going to divide that by n, which in this case is 200. So notice everything, if you want to zoom in, if you're using your phone right here, everything is underneath the square root. If it's not, you're going to get an error. You're going to get some other number. All right. So we get 0.0353. All right. So let's go ahead. Let's go back to the problem. And that's how they get the 0.0353. All right. So again, hit rewind and make sure you look at that again and practice it. Make sure you get the practice in because you want that muscle memory so you don't forget. Okay, so now we get into the good stuff because when we use the central limit theorem, let me fast forward a little bit, you're going to need the mean, right? And then you usually use the standard deviation as well. So we now know both. So part C, find the probability that more than 55% of the teenagers own a smartphone. So what's the chances of that actually happening? All right. So first things first, we want to make sure that we could say that this curve is normal, right? And so what we do to see if we have a normal distribution or approximately normal is we have two formulas to check, right? So first of all, we're going to multiply n times p. And when we multiply n times p, just like we did here, so we multiply our sample size times the proportion, the probability of that happening, which we got is 0.52, right? When we multiply that, we get 104. And what we do is we always compare it to 10 and we make sure that it's greater than or equal to 10, right? So that 10 never changes. So make sure you write that down because it's easy to forget and it's always 10. Don't worry about why. right now, just know that's what you're comparing it to. So that's the first thing. So far we're good. So check, it's greater than 10. The next thing you check for is you multiply n times 1 minus p, right? And then you ask yourself, whatever you get, so here's the math, plug into your calculator and you get 96. And you're like, oh, that is also greater than or equal to 10. So you have to do these two calculations. So make sure you do n times p and n times 1 minus p. Both of those answers have to be greater than 10. What that does is that tells us that we could use a normal curve. We could assume that this is normally distributed. All right, so again, make sure you write that check down, because if one of these isn't true, then we can't do everything we're about to do. We can't use the programs that we're about to use. All right. And what would normally need to happen is that will tell us your sample size is too small. And again, remember the central limit theorem tells us the bigger our sample, right? The bigger our sample size, the more normal our curve gets. All right. So what we do is like, all right, nice. We have a normal curve. My mean is 0.52. So there it is, smack in the middle. And what I want to see is what's the probability, what's the area to the right of 0.55? Because it says find the probability that more than 55%. So more than 55%, that's greater than. So we shade everything to the right here. All right. So there you have it. So this is what we're trying to see. Well, what program did we use before when we were trying to find the area or a probability or a percentage? That's right. We use normal CDF. So here we go again. We're going to use normal CDF. The only difference is now we have decimals. It doesn't matter. There's still numbers. The process remains the same, right? So we have decimals here. And when you plug in, notice when we're plugging in our mean, it's still 0.52. And the standard deviation is still the square root, right? That's what we found in part B here. Our square root is still, our standard deviation of the sampling distribution is still the square root of 0.52 times 1 minus 0.52 divided by 200. All right, so we're going to use that. Just in case you were wondering, where the heck did this 0.48 come from? That's just the 1 minus the 0.52. Because I know people click this button all the time, but they don't know where this number came from. That's just the complement, right, of this right here. Some books use the letter Q. All right. All right, so let's go ahead, let's dive in, and let's use normal CDF. All right, so I'm gonna bounce back and forth here because this is what these numbers are gonna be what I enter. So remember, when we're using normal CDF, this is our starting point. So we start shading at 0.55, and because I have a right tail, I keep shading all the way to the right. And what we said in our last video is our upper, when we shade to the right, is 1E99. All right, so make sure you make a note of that. All right, so the rules don't change. So let's take out our calculator and do this with me. So we do second vars, normal CDF. Our lower bound is 0.52. Our upper bound is 1 second EE right underneath sine, or some of you like to sin. I'm telling you, go to church. Just kidding. 1E99, comma. Our mu, what did we say our mean was? I think it was 0.52. Yes, it's, oh wait, I think this one was 0.55. Let me change this real fast. Because 0.52, I believe, was our mean. Some of you, I could already see you yelling. I could already hear you yelling. Our mean was 0.52. So go back and change that. You could always hit delete, right? Or you could start over, hit clear and start over if that's messing with you. And then our standard deviation is the square root of 0.52 times 1 minus 0.52. Close your parentheses, divided by 200 was our sample size. And then notice I'm going to get out of the square root. So I'm going to hit this arrow. And then I'm going to close everything and do this one. All right. So if you ever get an error, that just means one of your parentheses, you added a parentheses or you're lacking a parentheses, and it'll give you an error just in case that's happening to you. So we get 0.1979 if we round to 4 decimal places. So let's go back to our problem. And there you have it, 0.1979. All right. So what happens if, let's look at this. Part D, find the probability that the proportion of sampled teenagers who own a smartphone is between 0.49 and 0.55. So again, same exact thing. Always draw a brand new picture to represent every new problem. So we still have a normal curve. Our mean is still smack in the middle, but this time we got a lower bound, we got an upper bound here. And we're going to use normal CDF once again in our calculator, but the only difference is our lower bound is 0.49 and our upper bound is 0.55. Everything else remains the same. So let me show you a quick little calculator hack, right, doing this. So let me just remember 0.49, 0.55. All right, so let's go to our calculator. If you don't want to retype everything, just hit second enter and everything comes up again. So now I could just backspace and put my new limits. So I wanted to start this time at, I already forgot. What number did I want to start at? It was 0.49. 0.49, and then I wanted to stop at 0.55. 0.55. And everything else is the same, so I could just hit enter. And that way it'll just save you some typing, so you don't have to do this part all over again. So again, I just hit second enter, and I used my arrows to move around and change whatever I needed. And that's much faster. So we ended up with 0.6042. So go back to the other page here, and that's how they got 0.6042, right? Doing the same exact thing that I did. All right. The last little piece says find the probability that less than 55%. So now less than, again, you draw a brand new curve, and now we're shading everything to the left, to the left, to the left, of 0.55. All right, so we're shading everything to the left. So remember, when we shade to the left, our lower bound is negative 1E99. All right, and this time we're going to end at 0.55. So again, let's do our shortcut. Let's go back to our calculator. And using our shortcut, I'm going to get rid of this bad boy because we're no longer starting at 0.49. We're starting at negative. Again, make sure you use this negative button. Don't use the minus or else you'll get an error. So negative 1 second E99, and then we stop at 0.55. So we're good. So everything's set. Just hit enter, and we get 0.8021. But let's see if that makes sense. 0.8021. So let's go. Does this look like 80%? It sure does, because remember, 50% would be half, right? So this is more than 80% or 50% there. So that looks totally reasonable. All right, fantastic. And let's just double check. Boom. All right. So our last part, using a cutoff of 0.05. So again, we're going to compare our answer to 0.05. Would it be unusual if less than 43% of sample teens own smartphones? So would it be unusual if less than 43%? So we're going to look at the probability of that happening. And we're going to say if our probability, let's say our probability, our answer is 0.10, then we're like, no, that's not unusual. It would only be unusual, considered unusual, right, using this cutoff if less than 5%, less than 0.05. So if our answer comes out to less than 0.05, that tells us, hey, something unusual is going on. All right. So, and look, I like how they say an unusual event is one whose the probability of it happening is really small. right? So we're going to go ahead and we're going to find this probability. So we draw our curve. The 0.52 is right smack in the middle. 0.43 is right here. And we're going to shade to the left. So notice on our calculator, on our shortcut, we still keep the -1 E99, but now our upper bound, our uh, upper bound here is going to be this 0.43. All right, so let's use our shortcut. Let's share that screen. So I hit second, enter. And the only thing I'm going to change is our upper bound to, I think it's 0.43. Yeah, 0.43. Everything else stays the same. All right, hit enter. And notice it has this. So what we're going to do, if you ever get something like this and you want a decimal, just hit math and then decimal. And we get a commercial. And I have to guess which one to click. I don't remember. Is it this one? Dang it, clicked the wrong one. I think it was this one. There it is, our calculator's back. I don't know what I just bought. So we get 0.005. That is less than 0.05. So what that tells us is, yes, this would be unusual. So our answer, just like theirs, is less than 0.05 because it's 0.005. So we say we conclude that the probability that less than 43% of sample teenagers own smartphones is 0.0054. All right, so since this is less than the cutoff, we would consider this unusual. All right, and we're going to talk much more about that headed forward. But right now, what we're doing is we're learning how to be good users of this central limit theorem for proportions. All right. And then again, we're going to dive in deeper. So first, I want you to be good users, and then I want to show you some applications of, how can we use this? All right, we're headed there. Here's another good question. So this is question one, and sometimes, people before they start, they're gonna probably want to know. Let's say I'm gonna survey people. Well, how many people do I need to survey in order for this to be approximately normal? My curve here. All right. So let's look at this example. So you got Health Resources and Service Administration. They reported about 7% of people who have received kidney transplants were under the age of 18. So how large a sample of kidney transplant patients needs to be drawn so that the sample proportion p hat of those under the age of 18 is approximately normally distributed. So how many patients should do we need a sample here? All right, so write down this formula. So this is n equals, because notice what they're asking for. I should have left is how large a sample should be, right? So we go and we look at our first things that we check for, right? So for this to be approximately normal, these two conditions have to be met. This is what I was talking about earlier, right? N times P has to be greater than 10. And then n times 1 minus p has to be greater than 10. So what we do is we're going to use both of these formulas here, and we're going to use both of these inequalities, and we're going to solve for n in each case, right? And notice they give us a p of 0.02, so always change that to a proportion, to a decimal. So here's our two formulas, right, that I said we're going to use. And all you're going to do is you're going to plug in where you see P. I don't know why I said pen. You're going to plug in the number they gave you for proportion, 0.07, right? So here, again, from algebra, we're going to solve for n. So you divide by 0.07. So it did here, do this in your calculator, and you get 142.86. Right, over here, you're going to do the same thing. Plug in 0.07 like they did here. Subtract, you get 0.93. We're solving for n, so when you're multiplying, the opposite multiplying is dividing, so we divide both sides by 0.93, and you get 10.75, right? So both of these inequalities must be met. So notice the smaller number, 10.75, will not satisfy both inequalities. Because here, that number 10.75, yeah, that's cool here, but obviously 10.75 is not good enough for this one, because this one says it has to be greater than 142.86. So what you're gonna do when you get the situation, always go with the bigger number. That's the easiest way if you're having trouble understanding that. Just go with the bigger number. And what you do is you always round it up, because if we're talking about patients, you're not going to have a like half a patient or 0.86 of a patient. So we always round up to the next whole number. So the sample size in this case must be at least 143 patients. All right. So again, whenever they ask you to calculate patient size, use these two formulas, solve them for n, and then use the bigger number. All righty. So I hope that helps, folks. Hope you're having a great rest of your day. I'll talk to you later. Peace.